Welcome to our talk, Quantifying DNN Model Robustness to the Real-World Threats. This is a research work from Baidu Security. Deep learning technology has advanced rapidly in the last several years. It has surpassed human performance on image classification tasks, and it has also been doing very well in object detection, which is widely adopted in autonomous driving applications. And the accuracy is the one and only metric to evaluate the model performance. However, a carefully crafted adverse example can put deep learning models in danger. A slight unperceivable perturbation results in model misbehavior. Fortunately, so far, we haven't seen such any attacks on a large scale. In this talk, we argue that robustness is equally important as accuracy for safety critical scenarios. Real-world threats from either a glaring light, a tilt-shift camera, an obscured fast-moving object, or a malfunctioning camera sensor cell could also hurt the model. Thus, rather than jumping into the arms race with the malicious attacker, understanding the deep learning model robustness to the real-world threats is much needed for the AI industry. Our work tries to achieve two major goals. One is to make model-to-model comparison possible with regard to robustness. In this case, the robustness metric needs to be defined. The other is to make the robustness quantification a standardized procedure, where we need to deal with various safety scenarios such as brightness change, blurring effects, common corruption issues, etc. And also we need to support various use cases according to threat severity criteria where the robustness is measured upon. In the following slides, we will further discuss these respectively. In this slide, we show an original image and three perturbed images against three different models, ResNet 152, Red and ResNet, and Yellow v3. These perturbations are empirically found to be minimum in order to fool these models. And these models behave consistently and correctly against any perturbations that are smaller. In this example, ResNet 152 is the weakest one because a tiny change in the original image would be enough to fool the model. On the other hand, Yellow v3 is the strongest one because it would need extra effort to perturb the original image to deceive Yellow v3. Choosing the robustness empirical bound rather than a theoretical bound by using formal verification methods, mainly because large-scale production-level models cannot be easily verified. Now let us introduce our quantification framework. The first component is a pool of safety properties. In the physical world, we mentioned several safety violation use cases that could confuse the model. We simulate these cases by leveraging on computer vision technology. To summarize, we simulate 5 different categories: luminance, spatial transformation, blurring effect, common corruptions, and severe weather conditions. For each category, we further break that down. For instance, in severe weather, we simulate 3 different conditions: fog, frost, and snow. The second component is the threat severity criteria. When making the comparison, a criterion has to be selected. Different criteria have different complexity. For example, it is considered simple to do an untargeted misclassification, while it requires extra effort to conduct a target class misclassification within a target region of interest. Also, for various learning tasks, we can define task-specific threat criteria. The third component is the model pool. We support models built from various deep learning frameworks. In this case, we suppose the model ResNet 101 built from paddle-paddle framework is retrieved to be measured. The fourth component is the perturbation knob. This knob controls the amount of perturbations applied to the given input. When simulating safety properties, we introduce an influence factor epsilon in the range between 0 and 1. This epsilon appears in all safety property implementations. Here we only show 3 of those, and you can see for each of these implementations, the epsilon is the built-in parameter that influences the output of the simulation result. By linearly searching in this space, the perturbation knob can empirically identify the robustness bound. We refer the audience to the paper for more detail about the influence factor. Now let us put all the pieces together. Before quantification, we pick safety properties, threat criteria, in this case it's misclassification, and the model to be tested. Then, given an input image, the knob initiates with the smallest unit of perturbation. The resulting image is forwarded to the model. If it is misclassified, then LP norm-based distance between the adversarial image and the original one is calculated. If the model returns a correct misclassification, the knob increases the amount of the perturbation and repeats the process until the model misclassifies. With this framework, we can measure the DNN model robustness built from different deep learning architectures. We demonstrate model robustness results for the state-of-the-art object detectors, which is often a critical part of an autonomous driving perception system. Here in total, 849 images are selected. Each image contains an object that is significantly large so that all three object detectors predict that object the same as the ground truth with high confidence. For simplicity, the main object from each of the A49 selected image is bus. The threat criterion we used is target class misclassification, which means as long as the main object from the test image is no longer bus, it is considered a target class misclassification. We measured the robustness for all 15 safety properties for all three object detectors on the left figure. We also added ResNet152 for comparison purposes. The x-axis is the safety properties. The y-axis is the minimum perturbation measured in L2 distance. The higher the bar, the more robust it is for its corresponding safety property. As we expected, the object detectors are more robust than the image classifier. In the best case, it takes 6.4 times more perturbation over a safety property named additive uniform noise to fool YOLO v3 compared to ResNet152. On the right, we converted the result into a more understandable metric, fooling success rate. Basically, we took the mean minimal L2 distance of all the testing images over all the models as the threshold for each safety property. We regard it as a success when the amount of minimum perturbation needed to fool the model is less than the threshold. With this different metric, we confirm our finding that most of the time, object detectors are more robust than the image classifiers. Let us move on to a different application, that is online content moderation. It is one of the important tasks to prevent access to inappropriate content, such as NSFW, which stands for Not Safe for Work. We chose 3 commercial machine learning as service providers and randomly selected 400 NSFW images. And we ran through 10 different safety properties as indicated in the x-axis on the left figure. Since the output format of the cloud-based models varies, the prediction results can either be the logics or the class labels. Thus, we employ a combination of threat criteria including misclassification, original confidence loss, and a top K misclassification. Our goal is to find minimum perturbation to the input so that the perturbed one is no longer considered poor. The results indicate all the 3 commercial services are easy to break with a very small amount of perturbation in the magnitude from 10 to the minus 7 to 10 to the minus 4 in L2 distance. We also converted the result into a more understandable fooling success rate on the right. It confirms our findings that Model A is more robust than Model B and C. Finally, let us conclude our talk. Our proposed framework makes robust empirical bound comparison possible for production-level large-scale models. The results of ImageNet pre-trained classifiers, state-of-the-art object detectors, as well as the cloud-based content moderators encourages establishing robustness standards for AI's community and industry. We also proposed alternative property-specific robustness metrics other than LP norm-based distance. For instance, the rotation angles in positive and negative 180 degrees, the kernel size for motion blur effects, and audience are welcome to find out details in our paper. Last but not least, we open-sourced our benchmark tool along with the datasets in the following URL. Please feel free to check that out. Thank you so much. Now we are open for questions.